Well, about 50% of all the birds that breed in Europe migrate. But the vast majority of those birds probably don't fly above 1,000 metres. One of the features of the bar-headed geese is they have to fly through this very difficult and high landmass, which is a climb of nearly 6,000 metres. And we were wondering what the strategy was. How did they cope with the conditions? In high altitude, it's very cold, and the air is very low density, and this causes unique problems. So firstly, low density air makes it very difficult to fly. The wing doesn't generate much force from the air, so the lift required to support the weight and the thrust required to keep the bird flying fast is much harder to obtain, so they must flap the wing much more vigorously, and this causes a big increase in energy use. And the low density air means the availability of oxygen is severely reduced. But exactly how difficult these journeys are, we really don't know. And so that's what we were trying to find out. What are they doing and how do they do it?
Well, I can imagine bar-headed geese aren't the easiest animals to study, especially in migration. How did you go about obtaining this data or studying these geese?
A lot of the birds that do fly high usually climb up to the altitude that they prefer, and then they fly horizontally to make the journey economical. We thought perhaps the bar-headed geese would do that, but it looked like they were staying quite low to the ground. In the recent study, we used high-resolution pressure sensors to show the intricacies of their journey. We had to custom build devices that had a very large memory using a micro SD card to log the raw data from the electrocardiogram of the heart and from the accelerometers in 3 dimensions, and of course pressure and body temperature as well. Well, I have to give credit here to Robin Spivey, who was the main developer of these loggers. And that gave us a lot of raw data, which was then processed back in the lab a year later when we could capture the same birds and extract the devices. We had to set up a veterinary laboratory in the field and had a vet who did the implants for us. And what we discovered was that they were constantly climbing and then going back down again, and then they'd climb up again. So we were getting multiple ascents and multiple descents within a single flight. Sometimes they even threw away, say, 1,000 metres of climb. They would then descend 1,000 metres only to have to climb again later on. And we called this the roller coaster strategy. So that was the first thing. And then we were asking why this was. And we used the electrocardiogram signal to record heart rate measurements and also body motions using accelerometers to determine wing beat frequency amongst other measures and compare that with heart rate.
What conclusions did you draw from the relationships between all these different body measurements?
Primarily, heart rate was much lower than we were expecting. On average, if you took the whole journey, it was about 330 beats a minute. For birds, 330 was very low. So they were finding a route through the mountains where, on average, they didn't have to work that hard.
I guess if you're going to fly across the Himalayas, you've got to try and find a relatively easy way to do it.
Well, the simple route would have been to just go up to an altitude, stay clear of the mountains and the ridges, and just go over the top in a tailwind. When we looked at the energetics of what was going on, we determined that the cost of flying increases quite steeply as the altitude increases and as the air density decreases. And so it looked like it was cheaper in terms of total energy for them to keep staying low to the ground and taking advantage of the higher density air they could fly in, rather than stay high at, say, 6,000 metres and just fly at a constant altitude.
What do you think are the implications of this new insight into high-altitude flight?
I think what I would suggest is the future probably lies in the understanding the genetics that underpin the animal's morphology and physiology. We know animals don't seem to train. There's a recent paper been published showing that barnacle geese migrating from Spitsbergen show no evidence of training before the migration, and the bar-headed geese showed no obvious signs of training. They're just naturally fit at the right time of year. They switch on the right genes. And we know now from studies on mammals that you can induce these changes by switching on the right genes. And this has obviously got prospects for human medicine. And it could be that high altitude effects, particularly the medical side, the effects of low pressure, this causes humans to leak fluid into the lung or onto the brain and get acute mountain sickness. We're assuming that the birds just simply don't suffer from this. After all, they fly in a day up to 5,000 metres, no acclimatisation and no training. So there must be some possibilities there, I think, to understand the genetics of why they're different and what makes their physiology protect them.